All right, let's get into it. All around our planet, there are these incredible, invisible shields, vast rings of energy that protect us from all the craziness happening out in space. But what happens when a massive chunk of one of those shields just disappears? Today, we're cracking open the case file on a cosmic heist that happened right over our heads. So picture this. It's May 14th, 2019. Scientists are looking at their data and something is seriously wrong. A huge part of the high-energy particles that make up Earth's outer radiation belt is just gone. And I don't mean it dipped a little bit. In some places, it was wiped out almost completely. This wasn't a slow leak. It was a sudden vanishing act. The big question became, where on Earth, or off of it, did everything go?
To solve this mystery, we first need to get our bearings. Let's visit the scene of the crime and figure out exactly what we're dealing with.
What we're talking about here are the Van Allen belts. You can think of them as two giant cosmic donuts made of super energetic particles, mostly electrons, that are trapped by Earth's magnetic field. Now, the one we're interested in today is that outer belt. It's super dynamic, always changing and really sensitive to what the sun throws at us.
But here's the catch with these belts. They're a double-edged sword. On one hand, they're part of Earth's natural defense system. On the other, those exact same high-energy electrons are a huge menace to the satellites we depend on for, well, everything. GPS, communications, you name it. They can blast through shielding, fry sensitive electronics, and cause total system failures. So figuring out how they behave isn't just a fun science project, it's absolutely critical.
So what kicked off our whole mystery? It all starts right here. On May 14th, a massive gust of high-speed solar wind came barreling towards Earth and just slammed into our magnetic field. If you look at these charts, you can see that sharp jump in solar wind velocity right around 4 UTC. The impact basically squeezed our magnetic shield like a sponge, pushing its outer boundary way, way closer to the planet. And this is the aftermath. Just look at the data before that 4 a.m. mark. You see all that bright yellow and green? That's our healthy, thriving radiation belt, full of electrons. Then, poof, after the solar wind hits, it's like someone flipped a switch. The bright band is almost totally gone, replaced by deep blues and purples. We're talking a population drop of up to 99%. It's a true cosmic vanishing act, caught on camera.
Okay, so the electrons are gone. In any good detective story, you need suspects. And in this case, the scientific community had two main theories about what happened.
So let's meet our suspects. In one corner, we have precipitation. This theory says the electrons are basically knocked out of their orbits and sent spiraling down into Earth's upper atmosphere, like a kind of particle rain. And in the other corner, we have magnetopause shadowing. This theory argues that as Earth's magnetic shield got squeezed, the outer edge of the belt was just scraped clean off, with all those electrons getting swept away into deep space. So the big question is, did they fall down or were they thrown out?
And, finding the right answer here is a huge deal. As the researchers behind this study put it, knowing which process is really in charge and just how fast it can happen is absolutely critical. If we ever want to be able to predict and protect our satellites from this kind of thing, we have to know exactly what we're up against. To crack this case, our investigators needed a team on the inside, a network of observers that could see what was happening everywhere at once. And they found one in a pretty unexpected place. Get this. Our detectives are the very same GPS satellites we all use to navigate every single day. A fleet of 18 of them happened to be orbiting right through the Van Allen belts during this whole event. And because their orbits are spread all around the Earth, they gave scientists this incredible, global, real-time view of what was happening inside the belts, something a single satellite could never, ever do. Now, to analyze the clues, the team used a really clever forensic tool called phase space density. The easiest way to think about it is like this. If you squeeze a balloon, the air inside gets more compressed, but you haven't actually lost any air, right? Well, the same thing can happen with electrons in a magnetic field. This technique, PSD, lets scientists see past that temporary squeezing effect and track the actual, permanent loss of particles. It's how they could tell if electrons were really gone for good. And right here, this is the smoking gun. Each of these little charts shows data from a different GPS satellite. Okay, look at the ones on the left, from the hours before the solar wind hit. See how the data lines are pretty full and rounded? That's our healthy, normal belt. Now look at the charts on the right, from after the impact. Whoa, it's a completely different picture. The lines suddenly become incredibly steep, and then they're just cut off. It's like a cliff edge suddenly appeared in the data, showing that past a certain point,
There's just nothing.
So what does that mean? Well, that sharp cliff is the unmistakable fingerprint of magnetopause shadowing. It's exactly what you'd expect to see if a giant boundary wall, that compressed edge of our magnetic field, was just sweeping inward and clearing out all the particles in its path. The other theory, precipitation, just doesn't create a clean cut like this. So, case closed. We've got our culprit.
But, just identifying the culprit was only half the story. The next discovery was about the speed of the crime, and frankly, it's what would really change our whole understanding of space weather.
Using all that incredibly detailed GPS data, the scientists could basically start a stopwatch. They could pinpoint the exact moment the magnetic shield started to compress. That's the vertical red line you see. Then they could look for the very last time a satellite saw an electron in that region. That's the yellow line. The time between those 2 points, that's the getaway time.
And the result was just staggering. At the outermost edge of the radiation belt, the entire population of these high-energy electrons was completely gone in just 30 minutes, half an hour.
And get this, it didn't happen everywhere at once. It was more like a wave of loss that moved in from the edge. As you can see right here, at the very outer boundary, it took just 30 minutes. But a little deeper inside the belt, it took over 2 hours, 126 minutes, for those electrons to get wiped out. This inward-moving wave is just more powerful evidence for that magnetopause shadowing theory, a wall sweeping everything away.
So, we've solved a cosmic heist, and the getaway time was just 30 minutes flat. It's a fascinating story for sure, but the implications here go way beyond just this one event.
And this is really the key takeaway. 30 minutes is exceptionally fast. Before this, the general understanding in the scientific community was that these kinds of events happened over several hours, sometimes even a full day. Finding one that unfolds in less than an hour, well, that completely rewrites the playbook on how quickly our space environment can become dangerous.
Ultimately, this all comes back to protecting the technology that we have floating up there in space. These events can send electrons burrowing deep inside a satellite, charging it up until it shorts out. They can fry sensitive electronics and lead to total failures of the satellites that power our modern world. And if that danger can appear in just 30 minutes, our warning systems have to be just as fast.
And that leaves us with one final and really important question. We might have solved the mystery of the 30-minute disappearance, but in doing so, we've uncovered a brand new challenge. As our reliance on satellites grows every single day, this discovery is a huge wake-up call. The race is officially on to build forecasting systems that can see these ultra-fast storms coming before they have a chance to